So now we're going to look at projectile motion at an angle, and instead of projecting horizontally. And if you've played a bit of Angry Birds in your time, you'll know what I'm talking about. So this time what's going to happen is, instead of the initial vertical velocity being 0, it is going to have, if it's projected upwards, a vertical component. So how now will the velocity components change as we move through the air if it's projected at an angle? So if we have another look at our applet, our Walter Fender applet again, this time I've set the initial speed is still 5, but this time it is at an angle, and in this case it's 45 degrees. So for example, if we do, I'll just run that through, you can see how if it goes up and then down, so the minute it's released it will travel up for a certain part of the journey and then down, and again following that parabolic path. Now this time I'm going to show the velocity components. So as you would expect, the initial velocity of our initial upward velocity component is up and the horizontal is still there. Now once again the horizontal won't change, so watch the horizontal, watch the vertical components. I'll just do it in slow motion. And you can see it goes up, and just at the very top of our motion, what do you notice happens to the vertical? So we have, to start again, so as it goes up, that vertical velocity is getting less, and it reaches a point where it's 0, as would happen if you threw a ball directly up in the air. At the top of the motion it's 0. So one thing to see here is at the top of the motion there is only a horizontal component of the velocity. We resume, and you can see again the horizontal velocity is not changing, and the vertical component is getting bigger and bigger as then it gets towards the ground. So for the large part, the second half of that motion from the top down is exactly the same as horizontal projection. Now what I'm going to do is set now to go from the ground. So now it's just going from the ground at 45 degrees, and I'll just start again. So here you can see again at the top of the motion, just there, the horizontal velocity is the same but the vertical is 0. And as it goes down, that vertical velocity gets bigger again. Now because it's symmetrical, you'd hope that the time to go up would be the same as the time to go down, just as you would if you threw something vertically in the air. So again, that vertical velocity on the way up is getting smaller, reaches 0, and then increases again on the way down. And just as it was before, the sum of the two components is always going to add to the velocity at that point. So back to some notes, some things you need to take note of. If we project something vertically upwards, as you can see here, we've got this component and then you've got the two components there. I usually draw it as a triangle like that, as I have over here. So what we need to do is, instead of that initial component being 0 now, we have to work it out in terms of the angle of projection. So draw this and make a note of it. So your velocity vector can be composed of, resolved into the two components. The horizontal component is u cos theta, and I've called it u because it's initial velocity, and this I suppose also I'd usually label as the horizontal, and that would be the vertical component. So u cos theta would be the horizontal component and u sin theta would be the initial vertical speed. The horizontal would not change throughout the flight, so it's always going to be u cos theta. And once again, the acceleration is still 0. With the vertical components, this time, however, the initial speed is u sin theta, and at the top of the flight, there is no vertical component, it is 0. And there is only that horizontal component of the motion. So again, it's still subject to acceleration due to gravity, and the velocity at the top of the flight is 0. So once again, when we approach these questions, we're still going to break them into components, but we're going to break usually, we'll approach these questions by breaking up the motion into the upward part of the journey and the downward part of the journey. So let's have a look at our stunt car, and it's driving over some water or river, 50 metres wide, and its initial speed is 22 metres per second. We've got the angle there as 40. So how do we approach this? Well, this situation is the simplest of our horizontal projection in that it's symmetrical. So our initial speed when it leaves the ramp is v, and that can be broken into the two components. So one of the first steps to do is to work out what are the vertical components and what are the horizontal components that we know. So firstly, in the vertical direction, what's my initial speed? And we know that that in this case is always going to be u sine theta, or in this case 22 sine of 40 degrees. And I won't round off just yet. That gives us about 14 metres per second as the initial speed. I know that the acceleration is also minus 10, and I'm going to leave it at negative, particularly in these the projection at angle. Definitely keep the negative sign. So I know that I don't have the time of flight yet. I don't have any vertical distances either. So in the horizontal direction, what we do know is that the displacement is 50 metres horizontally, or 25 metres if we go halfway. So just put over here that we don't know the time. I know the horizontal direction. I also know the horizontal speed, which isn't going to change, and that's going to be 22 cos of 40, and we might need that later on, so I'm going to work it out now. 16.85 metres per second. Alright, so will a car make it? So in order to know that, will it make it, at the moment the actual distance of the river is 50. I actually don't know if that's how far the car's going to go. So we do need to actually work out that horizontal distance travelled, but we need to check that it's going to have to be greater than 50 metres. So we'll need to work that out later on. But first of all, probably the thing that we often need to find first is time. I don't have the time. So let's work that out using our equations of motion. If I want to find t, I've got a, I've got u. Some possible equations I could use here is if I consider only the top half of the journey, then if I consider just the upward part of the journey, so if I just consider the upward path, then at the top I know that the v is 0. So therefore, if I use v equals u plus at, or rearranging, then I can find the time, because what we'll be left with is at 0 at the top. I've got the initial speed is 14 minus 10 times t. So t is going to equal 1.4 seconds. So therefore, if I know the time up, I also know the time for the whole path. So the total time would be double that, which would be 2.8. So therefore, the total time would be 2.8 seconds. If I know the total time of the journey, then, and I know the horizontal speed, then if I come back to my horizontal components and just consider that the velocity is going to be distance on time, or let's find the horizontal range, is going to be my horizontal velocity times the time. Working that out, when we work that out, our final distance is equal to 47 metres. Our car is not going to make it. So our problem here is our car won't make it because the distance travelled means he is not going to get all the way to the other side. He's going to do something like that and probably end up landing into the barrier. So when we look at our projection at an angle, we need to consider, break it up into two parts. If it's symmetrical, it's a bit easier because we know that the time up is equal to the time down in the journey. So that's just a bit of an introductory problem to our projectile motion at an angle. We'll just have a look at one more problem. Again, this is symmetrical. If you have someone jumping, for example, here we've got their initial speed, the angle, 30 degrees. How high would they jump? So again, the first thing to do is always consider the vertical components and then the horizontal components. So I'm just going to do the vertical and then horizontal. So I'm going to ask myself, okay, what do I know in each case? So vertical here, I know that the initial vertical component is going to be 7.5 sine 30. So when you work that out, that's 3.75 and that is up. I also know the initial horizontal speed, which of course will remain the same, which is going to be 7.5 cos of 30, and that gives us 6.5. I don't have much else at the moment, so one of the questions you ask yourself, well, what would be the height gain? So to do that, I would only consider the vertical. I have an initial speed, and at the top of the motion, of course, I would know that the final vertical component would be 0. So therefore, in order to find the vertical distance travelled to the top, which equation could I use? Because I have an initial speed, a final speed, distance travelled. Well, we could do something like use v squared equals u squared plus 2ax. So the final is 0. The initial was 3.75 squared minus, because it's negative 10. Don't forget it's assumed, but I've always got a, minus 2 times 10 times the distance travelled up, and if I rearrange that, therefore the distance travelled would be 3.75 squared over 20, and that means that when you work that out you get a distance of 0.7 metres, and that makes sense because if someone's doing a long jump they would go a certain distance up. So that's the distance travelled. Again, how would you find the time? Once again, we could use the same method. If I wanted to find the time of the flight, the time that they're in the air, again, I'd break it up into just the upward section. So if I just consider the upward path, the velocity at the top is 0 once again. So therefore I need to find time. So probably there, given that I've got u, again I could v equals u plus at, final 0, initial is 3.75 minus 10t, so therefore the time up would be 0.375 seconds. So therefore the total time would be 2 times that, 2 times 0.375. And when you get that, we get 0.75 seconds. Again, to find the horizontal distance travelled by that person, again using the horizontal distance, the horizontal speed, I know that the horizontal speed is 6.5 because we worked that out before, and I need to find the horizontal distance travelled, so that would just be the velocity again times the time. And now that I've got the time, often you're going to need to work out time in order to find the distances, so that would be 6.5 times 0.75. So they go 4.98 metres. So just to sum up again, the key things are on the way up, the time to go up and down is the same if it's a symmetrical path, and often we break the motion up into the upward section because the velocity at the top is 0. That enables us to find the time taken to travel up, and then we double it to find the total time of the journey.